Welcome back to SanfordFlipMath. We are actually starting Chapter 3, so you can disregard that. The reason that's there is Chapter 3 is all about derivative, and another great word for derivative would be instantaneous rate of change, slope of a curve at a point, etc., etc. So I just want to kind of draw your attention to this. Now, this is the list about instantaneous rate of change and derivative, etc., that we've talked about before. So I'm just going to kind of key these guys together because all of this stuff goes together. Okay, not the same thing as average rate of change. Average rate of change is like old school slope, like Algebra 1 slope. So we're not talking about that. We did that in Algebra 1. We've talked about it a little bit here in calculus, and it'll come up periodically here and there, but Chapter 3, the entire focus of Chapter 3 is on derivatives. It's going to start off with the definition of derivative, which we've really pretty much done already from Chapter 1, but we'll recap again. And I just want to point out notation. Again, this is from our calculus book, the Finney, Demana, Waits, Kennedy book on page 101. Excuse me. And this is real common notation, and similarly, f prime, so that's read f prime of x or f prime, y prime. Remember that derivative is like slope. Okay, so if I go to average rate of change, it's like change in y over change in x. So this is that little, that Greek letter delta, which means difference. It sounds like a D in English. So the difference between the y's over the difference between the x's. Well, this notation is really related to that. So this is an English D and an English x, and the idea is, again, difference between the y's over difference between the x's. But what we're actually going to focus on, as you know, as that difference between the x's gets closer and closer to 0, as that separation between the 2 points on a curve gets closer and closer to not separated, it becomes derivative. In terms of how we are going to say this notation, that's dy dx, that's how we are going to read that. Or in other words, the derivative of y could be the derivative of f, the derivative of whatever, with respect to x, okay, because we might have different variables. So similarly, this might be dh dt sometimes if it's the derivative of height with respect to time or something like that. Okay, df dx, and again that goes back to the idea of f of x being y, which is also the same thing as this. Okay. All right, so this is just different notations, and we'll see variations of these notations throughout, but I just wanted to make sure you saw it. Okay, well, this looks like an exciting screen. There's nothing there yet. So f of x, let's just start with a pretty normal function. And if we're going to find f prime, that means we need to do derivative. Okay, now you might recall, okay, and let me just pop back over here. Okay, here it is. This is that derivative again, and I know you're not happy to see it again. We're going to see it for basically the beginning of Chapter 3 again, and then once we get to 3.3, we'll be focusing on the shortcuts, and you'll be much happier about that. So we're going to do this again. Okay, so f prime is f prime. Okay, so here we go. So f prime of x. Okay, so I'm going to do the limit as h approaches 0 of f of x plus h, sorry, f of x plus h. Okay, and so this is going to be my f of x plus h. So here's my x plus h minus f of x. Okay, all over h. Okay, so just a reminder, this part right here is my f of x plus h. This part right here is just f of x. Okay, now Sanford's being mean to you now because he actually did a cube, and I'm going to carve out a little space over here. Just a reminder that the third power means I have to multiply that times itself a total of 3 factors. Okay, I'm going to multiply these guys first, so I'm going to write x plus h here. Okay, and I'm going to distribute, or FOIL if you prefer. Okay, now I need to distribute the x, and it's got to come across all 3 of these. Okay, then I need to distribute the h, and again, it has to come across all 3 of these, and I'm going to line up like terms as I'm going along. Okay, so this first one is hx squared, also known as x squared h times 2xh, and then h times h squared. Now again, I like to line those terms up so that I can see what's going on. It's easier to do this part now. Okay, all that was x plus h cubed. Okay, so now I'm going to come over here and continue on with my little derivative. Okay, so here's my x plus h cubed. That's that, plus 1, minus x cubed minus 1. Now, again, that minus 1 is there because when I subtract this group, I have to subtract both of them. Okay, all right, let's do some adding up, combining of like terms. So I see an x cubed here and an x cubed here. I see a 1 and a negative 1, or a minus 1. Okay, so you can track what happened. Everything else has an h. Okay, so the limit as h approaches 0. Okay, here we go. And remember, we haven't taken the limit yet. And I know some of you would have done what I'm about to do on the last step, and that's fine. Divide by h, divide by h. Now divide by h, there's still 2 of them left. Divide by h. Okay, so again, I still have not taken the limit yet. Okay, so this is now 3x squared 3xh plus h squared. Okay, sorry I missed my 0. I know somebody was sitting there going, you missed your 0. Got it. Okay, now I can take the limit. See, before I couldn't just plug that 0 in because it would have made it undefined. So now I actually can. Nothing on the first term. That term becomes 0. That term. So this goes to 0. This term goes to 0. All that's left is 3x squared. And I know what you're thinking. That was a lot of work. Yep, sure was. Okay, so sometimes you're going to have to work a little bit, and that's, well, welcome to life. Okay, let's continue. Okay, let's do another one. I just want to do another example. Okay, let's do the derivative of 1 over x. Okay, now this notation is again the same thing. This just means we're doing derivative with respect to x. Okay, and of 1 over x. Okay, so that's all this means. Okay, so it's the same idea as before, and I know somebody's going to say, but I like the other notation. Okay, but you have to get used to lots of notations. Okay. Okay, limit as h approaches 0 of f of x, so 1 over something minus, sorry, f of x plus h, 1 over something minus f of x itself, all over h, and that something is x plus h. Okay, you'll be trained professionals at this soon. Okay, so this, I'm going to call this y prime, okay, with the idea that it's the derivative, okay, equals limit as h approaches 0. Now, here's the issue. How in the world do you combine these? Okay, well, we got a couple of options. I'm going to go ahead with what I consider probably the most common. The least common denominator for this thing has to have all of the factors of all of the denominators. So that means I would like this to be x times x plus h. I would like this to be x times x plus h. So I'm multiplying the top and bottom of this fraction by x plus h, so I'm really multiplying by 1. And so now I have a common denominator. Now, once I have a common denominator, I can do some stuff here. So this top fraction has a single denominator now. X times 1 is x minus, now this is going to be, I'm going to go ahead and distribute that minus 1 on both of these, or that negative 1. So minus x minus h. Okay, again, I can't put h equals 0 in yet, I can't substitute yet to do the limit. Okay, so on the top, okay, for all of you following along at home, okay, x minus x is nothing. Okay, so in the numerator now I have negative h over, okay, sorry, I don't like that where I put it. Okay. Negative h over x times x plus h all over h. Well, a couple of ways to handle this, but basically this is h over 1. So I'm going to change this into multiplication. Limit as h approaches 0. This becomes negative h over x times x plus h times the reciprocal of this guy, so that now I can actually divide out that h. Oh, I'm getting excited. This is really close. And I'm just going to rewrite this before I do the next step, just because, again, I don't want there to be issues. Okay, now we can actually do the limit. Okay, so I can actually put the h equals 0 in for h, because it doesn't make it undefined anymore. So this becomes negative 1 over x times x, which some of you would like to call negative 1 over x squared, which I think is a fabulous idea. Now, I want to just take a little spin here, because I know, again, this is a lot of stuff, and I want to give you an opportunity to be able to check yourself. Okay, so this is the rule that still we don't know yet. Okay, so if I have y equals ax to the n, if I want to do the derivative, the shortcut for this setup, do n times a times x to the n minus 1. Again, this is just, for us right now, I'm just showing you this so you have a way to check this. I need you to have a firm foundation in where this comes from, and that is this long difference quotient thing that we've been doing. Okay, but I still want you to be able to check this. Okay, now your question ought to be, why are we talking about that for this? Well, because this is a power function. Isn't that x to the negative 1? So if that's true, then y1 should be negative 1 times 1. So this is for y prime. Negative 1 times 1, so negative 1 times x to the, remember we subtract 1 from the exponent. Well, what's negative 1 minus 1? And that can be written like this. Okay, so this is a rule that I know you have an awareness of, because I have, quote, not mentioned it before. Okay, I still need you to be able to do the difference quotient thing, the big old long limit as h approaches 0 thing. Okay, when we get to 3, we can use that rule, and we'll stick with that rule. Okay, so there will be one question on this first test from chapter 3. We'll probably have 3 different tests from chapter 3, maybe two or three. But the first test will have a question that's about the limit definition. Okay. All right, let's see what's up next. Ooh, look at that. That's pretty. Okay, I want to talk a little bit about derivatives at a point. Derivatives at the endpoints. And so what I want to do first, though, is talk a little bit about derivatives from a graph. And I need you to remember that derivative basically means, in its basic idea, slope at a point, slope of a tangent line, slope of whatever. Okay, if it's a curve, slope of a tangent line. So I guess my first question is, what's the slope right here at that point? And so this is a graph of y equals f of x. Okay, and so the idea is that I want to know f prime of 0. So that works just like regular f of x notation, f prime of 0. So what that means, slope, I want the slope of f of x at x equals 0. Well, what's really cool about this is if you understand what this notation is asking, this is probably the easiest problem you're going to see the whole chapter. Well, let's count together. Down 1 over 1. Down 1 over 1. That slope's negative 1. Okay, assuming these are numbered by 1s, and so are these. Okay, so this slope for this whole section has a slope of negative 1. So the slope at 0 is negative 1. Isn't that exciting? That's good stuff right there. Okay, simple, simple, simple. Okay, so what's the slope at positive 1, at x equals positive 1? Same thing, negative 1. Okay, the slope at 2.5 would be positive 1. Okay, so f prime of 2.5 is 1. Okay, so now the trickier questions are these. What about the slope at 2? So I want f prime of 2. I know the slope on this side is negative 1. I know the slope on this side is positive 1. So what's the slope at this corner? Now this is really where the limit issue kind of pulls back in. If I'm going to say the limit as h approaches 0 of all that stuff, if I'm going to say that, then the idea is if I do that, that's from the right. If I do this, that's from the left. And in order for a limit to exist, remember the two-sided limits have to match. So if the limit as x approaches a from the left equals the limit as x approaches a from the right, then the limit as x approaches a is equal to whatever those were. Okay, well that's great. What's that mean for this? It's based on a limit. From the right, that limit is positive 1. From the left, that limit's negative 1. They don't match. So this does not exist because it's based on a limit that doesn't exist. Okay, now having said that, remember what we said about limits at endpoints. So now the question is, what is, based on what this function is, what is f prime of negative 2? Well, I know that the limit as h approaches 0 from the right for this thing, I'm talking about the right-hand slope, the right-hand derivative. That looks like it's rising 4 and over 1, so that'd be 4. Okay, and I'm not even doing the whole definition, but you understand that slope is derivative. Derivative is slope. Okay, the limit as h approaches 0 from the left of all that stuff, well, it doesn't exist. So the question is, why doesn't it exist? There's no function there. It's not part of the domain. So I guess we're back to, why are we even talking about that part? It doesn't apply. Okay, there's nothing over here. So I really don't need anything to match. There's nothing to match with. Okay, with which to match. There I go. We can do math, but not match. Okay, so ultimately the moral of the story is f prime of negative 2 is 4. It doesn't have to match on the other side. Okay, so if we do the same, by the same logic, f prime of 3, okay, let me make some room here. Again, this is at the end point. Okay, so that we're talking about derivatives at the end points. So we're at the end point now. The left-hand derivative is 1. That slope is 1. The right-hand derivative doesn't exist. Don't need to match it if there isn't anything. So therefore, I'm just going to say 1. Okay? All right, so derivative at an endpoint. Okay. All right, well, this pretty much wraps up the heart of what we need to deal with for today. This is 3.1. This is technically going to end up being 3.1a because we have to spend some time talking about just looking at graphs and graphing derivatives. And so we will pick this up again next time with 3.1b. Thank you very much. Appreciate you being here.